Hello, all. Good morning. I'm very pleased to welcome you to today's CAE seminar by Professor Muhao Chen. The topic is lightweight deployable tensegrity systems for space explorations. Professor Chen is an assistant professor of aerospace engineering at the University of Kentucky. He is the PI of the tensegrity lab. Before this, he was a postdoctoral researcher in aerospace engineering at Texas A&M University, where he also earned his PhD in the same department in May 2021. Dr. Chen's research is dedicated to the design, mechanics, and control of lightweight deployable space systems for extended planetary exploration. This research includes creating foldable structures, robotics, which are optimized for landing, locomotion, self-deployment, in situ assembly, etc. The focus is on using minimal resources and innovative deployable paradigms, as an example, like tensegrity and origami. His research on space habitat with 1G artificial gravity for human space travel and life beyond Earth has received significant public recognition. So, thank you very much, Dr. Chen, for doing this. We appreciate it very much, and the floor is all yours. Thank you.
Thank you. Thank you. It's really glad to be here, and thank you for your kind introduction and invitation. So let's get started. So my research goal is to design space systems for humans' deep space explorations to uncover the unknowns. I think this is probably the only way that only affordable way and we explore deep space explorations in a fast and massive manner. And while I'm presenting some of my theoretical work, I'll also go through some of the applications shown here. So this is a space habitat. It's the inner support structure is a tensegrity structure. And so this is a habitat that can housing 8,000 people. And the whole habitat is rotating about this axis, also shown here. And this is an inner area of the habitat. It's a green park, and crops are growing on these two sides. Humans live on the lateral side of the space habitat. So it's basically on the edges of this circle. This is a space antenna. As you can see, that is a deployable structure that we can pull the strings to have different radius of the antenna. And this is a tensegrity actuated origami structure, I would say, but used for space solar panels. As you know that solar wind is a great damage to these kind of structures. So when that come, we can unfold our solar panels in a very compact configuration. And as you can see that we can use this kind of structures to support, to build a biosphere lunar base. And I'll discuss more details about these kind of structures. So today my topic is lightweight deployable tensegrity systems for space explorations. So first is why space systems need to be lightweight and deployable. As you know that we have very high launch cost from the rocket side, and we have very limited rocket size. And these two hard constraints limit our design to find better structures and materials and systems. So they are asking us to reduce the mass and volume. And these two constraints are pushing our aerospace and academia to find better materials, stronger structures, and more efficient systems. So why tensegrity is a good candidate to solve the two proposed challenges? Biology system perhaps provide the greatest evidence that tensegrity structure is one of the most efficient structures in nature. So for example, from the nanoscale, we can see that these living cells using microfilaments and microtubules as tensile and compressive members to control the traction of cell surface. And the DNA bundles have this kind of compressive and tensile elements. And for the macro scale, our elbows and even in the molecular structure of the spider fiber, you can see this compressive and tensile members. So here's the definition of tensegrity. It's a network of bars and strings where the bars are in black and the strings are in red. Since all the structure members are one-dimensional loaded, so we can place the materials along the load path to save mass. So it would have high mass efficiency. We don't need to place materials that is orthogonal to the load path, right? And since the deformation along the structure members is one-dimensional, so that gives us a more accurate model than we need to bend the structures or bend the materials. So the uncertainty is only in one dimension. And we can tune the pre-stress or the length of the structures to have tunable structure properties. So for example, we can change the shape by changing the length of the strings here, or we can change the pre-stress of the structure to increase the stiffness without changing the shape. And the soft strings and the structure can be used for energy absorption. And the last one is, by changing the length here, we can change the shape. All right, let me give you a very simple idea that why tensegrity is can be a better structure than continuum. So for example, from our engineering mechanics, we can see that. So if we apply a buckling force here, the bars will be buckled, right? And the minimum mass of the single bar that take this force before buckling or at the critical load of buckling is given by this formula. So this is the least mass of bars to take this F. And for a tensegrity structure, if we do the same math, the 4 bars are at the critical buckling load, and the strings are subject to yielding. This is the least mass of the D bar. If we use alpha angle, which is this one, to be 10 degrees, and use steel bars and strings, this mass, the continuum is 1.4 times of the tensegrity structure. So that is saying our tensegrity structures can save mass. And another advantage is we can tune the length of this string, so the whole structure can be in a very compact volume, right? So it's both lightweight and deployable. So the tensegrity structure has been used for a lot of applications. For example, the smart structures, aerospace. So NASA designed this kind of lander that can land and locomote. And the metal materials, and even in soft robotics. Let me play the video first. So for the lightweight structure, for this tensegrity network, we can store in a very compact volume and do the right things to the upper and lower strings. We can have a very large space structure. But as you can see that there are so many degrees of freedom, and the dynamics and control of such flexible structures are the main challenges in our next generation space systems. So here's the outline of my research. First is given the loading conditions, how to design a structure that is lightweight and deployable. So it's a structure to get the most mass efficient topology. And after we have the structure, the critical thing I'm looking at is what is the least mass to take the given loading conditions. And after we have the structure, and how to do the precise dynamics modeling. And while we have the precise modeling, Another point is how to use the least computational cost to simulate the dynamics and do the analysis. And after we have the structure and dynamics, how to do the control. The control has two critical points, which is passive and active control. And the critical question I'm looking at is how to use or how to design the structure with least dampers, sensors, and actuators. So for the first topic, lightweight and deployable structure design, tensile structures have provided 5 fundamental solutions to engineering mechanics: compression, tension, torsion, cantilever, and simply supported. So what we do is, for example, if I need to design a tower to support a payload on the top, so what I do is this kind of structure is called the T-bar structure, which is very mass efficient in taking compressive load. And we can find the optimal structure of this one. And in the last iteration of this structure, we can replace this horizontal bar with this kind of D-bar. We call it D-bar structure. And in this way, we can have a lightweight and deployable structure. So by changing the length of the strings, we will be able to deploy the whole structure in a stalled configuration. And the previous work on the lightweight structure design is they pre-assume that, for example, all bar buckles and do all the the lightweight structure design. And the other side is they pre-assume that all bar yield and do the minimum mass design. So what I do is I remove all these two pre-assumed conditions. So for example, if we want to do this kind of structure, combine these two together, these two assumptions may not valid, right? So here's the algorithm. I developed a general approach to find the least mass of any structures subject to any nodes. So for example, this is a nonlinear mass equation. The mass of the whole system equals the mass of strings subject to yielding, and the mass of the bars subject to yielding, and mass of the bars subject to buckling. Because we don't know which bar are yielding or buckling first, so I introduce a label matrix, which is given here. So this is telling which bars are buckling. So identity minus Q means the rest of bars are subject to yielding and subject to our statics equation. And we can formulate this kind of optimization problem. As you can see, mass is our objective function to get the minimum value subject to the statics equation plus gravity. So gravity is a function of mass. So it's a coupled nonlinear optimization problem. And often we have some other, for example, the stiffness requirements to the structure. So the pre-stress, so X is a force density, which can note the physical meaning of the stiffness. So it can be greater or equal than some bound to the structure. All right, so by solving this problem is we presume that all bar buckle at the first time and do the iteration until we find a global solution. So there's no pre-assumptions needed. The problem is globally solved. So for example, here's an example of the robotic arm and subject to cantilever load. So this is how the robotic arm looks like, and this is a gripper. This is the gripper here, and we apply a force at the tip, and the force is 1,000 newtons. And the result is showing that, another advantage we have is to decrease the number of strings used in this kind of tensile system, we can cluster some of the strings together. So for example, 1, 2, 3, these 3 adjacent strings can be using one cluster string to manufacture this kind of structure, right? So the result is showing that when we are using hollow bars, we can reduce match mass. So for example, 2.7 is much less than 3.6. So that is saying hollow bars are more efficient than solid bars. And if we use cluster strategy, so the advantage is we can reduce the number of strings, but the payment is we need to increase the mass of the single of the structure. And another comparison is that gravity. So consider no gravity and consider gravity. As you can see, the values are pretty close. So gravity influence is negligible, and the hollow bars are less than solid bars, and we can decrease the number of strings by using the cluster strategy, but we have to pay the mass. And moreover, we can get the modes and frequency information from the analysis. All right. As that algorithm can be applied to a more general design of structures. So for example, we design the structure from 1D. So the structure members, bars, and strings are from 1D. And then we can make 2D units and then combine them into a 3D structure. And this kind of structure can be used for, we call it double helix tensegrity. It can be used for compression, tension, inner pressure, torsion cantilever, and simply supported out pressure. And all these kind of loads, we can find the optimal combination of the complexity, where complexity is defined as the P is along the horizontal direction and Q is along the vertical direction. And the real applications is basically the combination of these 6 loads. So for example, the biosphere, the lander, the membrane, and a wide range of other structures shown here. So these are calculated by the previous developed algorithm. All right. So as you can see that tensegrity has many benefits, but the another disadvantage is it has no cover. So we ask for another deployable structure for help, which is origami structure. So the tensegrity structure is mass efficient. It has accurate model. It can do the shape control, but there's no cover, and we have very complicated joints when the structural complexity goes very large. And for the origami system, as you can see, that it can also achieve complicated shapes. It has compact size, and it has metamaterial properties. But the urline, because it is a paper folding kind of paper folding structure, right? So the stiffness is urline low, and the transient dynamics is not urline controlled. So what we can do is we can combine this tensegrity and origami structure to have this integrated system. It can achieve both lightweight, deployable, and there's a lot of redundancy in the bars and strings, and it can achieve multifunctional and metamaterial properties. And also we can tune the structural parameters and change the size of the structure. I think one of the reasons that tensegrity or the origami structure didn't come to engineering was because when people looking at this kind of structures, they were saying it is too complicated to model, right? So there are a few attempts to do it. So the mechanics model of the tensegrity is people, for example, using rigid bars and elastic strings to model these kind of structures. And and some other people do the lumped mass model. So lumped mass is you have a bar, and we can use 2-point mass to represent this continuum bar. And some other people use, for example, Mojoko and others to do the simulation. And the previous work on the origami structure is some people use a rigid body model. So they pre-assume that the panels here are rigid, and the bar hinge model. So this panel is modeled as a bar, and the panels in between the angles, they use a hinge to model the rotational stiffness. And some other people also go to FAM model. But I'm going to show you that just in one page, how simple the math can be to precisely capture the dynamics of the integrated system. So I removed the assumption of the rigid body model. So the bars and the strings are allowed to have elastic or plastic deformation. And I'm using the nodal coordinates as a generalized coordinates. So it is minimal coordinate and very easier in linearization. And because we have an explicit model in the nonlinear dynamics and linear dynamics, so we can be able to do complex control problems. So for the tensivity structure, the bars and strings are allowed to have elastic or plastic deformation as given here. And for the origami panels, I'm using the bar hinge assumption. So this is a bar and this is a hinge. And just in one page here, you can see that these are the defined nodal coordinates, mass matrix, and gravity constant. And for the tensivity part, we need to define some of the nodes are free and some of the nodes are constrained. And this connectivity denotes how the bars and strings are connected. And for the origami part, we define the angles between the two panels and initial angle between the two panels and the moment between the two panels. And using the Lagrange method, so we can formulate the kinetic energy given here, and the stream potential is given here. Since we are capturing the elastic and plastic deformation, so it's an integral form. So if you only consider the linear elastic deformation, it should be a 1/2 k delta x squared. And the gravitational potential given here. And the hinge in the origami is the potential energy is given here. So by using the Lagrange method here, we can get the explicit nonlinear dynamics of the integrated system. So this is integrated dynamics. As you can see, the first part goes to tensivity, and the second part goes to origami. So this kind of dynamics can separate into two separate forms. So you can do the tensivity dynamics, and this is tensivity statics by removing the time derivative terms here. And also for the origami, we can go to the second row of the equation. So the dynamics and statics. Since, as you can see, that we have a lot of degrees of freedom in the bar and hinge or the tensivity structure, and the computational cost is really high. For aerospace systems, we need to have very fast computational capability, because when we do the real-time control, it's better to compute the dynamics as fast as possible. So one traditional way we can do is we do a coordinate transformation. So for example, we can write it into the model coordinate and throw away some of the states. Then we have a radial solid model. As you can see that when we throw away some of the states, the dynamics information is lost, right? So what we do here is, as we can see, when we increase the model size, our model becomes more precise and precise. We'll have less and less dynamics error compared to the physics. But if we put these large size models into the computer, sorry, we'll have a large computational error. So the combination of the two errors, the computational error plus dynamics error, will have this kind of shape. It's a parabolic shape. That is saying there exists a model size that has the least simulation error and the least computational cost. So here's how we do it. We write the dynamics of the physical system and consider the computational cost into computation errors into this physical system and assemble these two systems to compute the error covariance matrix of the two systems. And by solving these two Lyapunov equations, we'll be able to find what is best model size to have the least total errors. And here we show the results of the tensegrity and origami dynamics. So for example, this is origami sheet, and this is a tensegrity frame. And we can put these two structures together. And by actuating the strings, we can have this foldable tensegrity structure, tensegrity and origami integrated structure. And during the process, we can get the other information. So for example, the stiffness in different directions, and we'll have a smooth folding when stiffness is guaranteed. And for the dynamics modeling of the tensegrity structure, we shown here. So we apply a force at this point, and by given different materials, so this is linear elastic, multilinear elastic, and plastic. And the result is showing that this model is very accurate. We compare with ANSYS. For example, the natural frequency compared to the ANSYS is like 10 to the minus 15. So we can do the dynamics and also the statics of the structure. And as you can see that this is an explicit model. It can integrate structure and control because we can put this dynamics equation with control equations together. And what ANSYS cannot do is they cannot cluster cables, and they cannot consider cluster cables with pulleys and the frictions that our model is able to capture that. For the model reduction, here's an example. We give a 6-bar prism. And as you can see, if we use a AB computer, the total error looks like this. So that is saying the computational error is dominant. And when we use 20-bit, there exists a model size 6 that gives us least total error, which is computational error plus dynamics error. And when we use 64 bits, as you can see, that computational error is negligible. So that is saying for our laptop computers, for example, 64-bit, the model reduction is maybe not necessary, but for the onboard computers in spacecraft, it's normally like 16 bits or 20 bits. So if we use this kind of method, we can reduce the total error, reduce the computational cost, and increase the performance for free. And the last topic is for how to control this kind of highly flexible space structures and robotics. So the control has two parts. One is passive control, and the other is active control. For the passive control, is given any instructions or given any signals with an energy bound. So, for example, we have wind, we have impact, we have earthquake to the launch pad, and how we are going to design a damper such that the structure can sustain in its equilibrium state. So what people normally do is they do a structure design here. They come up with some damper design based on their experience, and then they run the Monte Carlo simulation. So basically, it's sampling, give a range of the signals and sampling the signals to generate millions of signals that can put into the computer, put into the structure, and see if the performance can be satisfied or not. So for example, if they design a damper and put all the worst cases into the structure and see that performance is satisfied, the design is complete. But as you can see that we cannot know what is a better damper design, or what is the least damper we need to use for the structure. So if the damper design doesn't work, we'll have to rerun the simulation, rerun the Monte Carlo methods many times to see if the design is complete. And another thing is after millions of tests, we cannot still guarantee that we can capture the worst case. So what I do is um, this is a problem statement. Given any signal with an energy bound, so the any energy bound is given by this function here. No matter what the signal looks like, it can be a sine wave, square wave, or any shape of waves as long as the energy is bounded. So this energy bound is usually defined by the integral of the signal over time. And normally we have a performance bound. So we want, for example, this displacement of this object to be a bounded value. So the supreme, which is a peak value of this output, I'm showing the picture here. So this is output signal, and this is a peak value. So this peak value is bounded. For the structure, it can be the peak displacement of my structure members, or the peak stress structure members can take. So using the control theory, it's a L2 to L infinity theory. That is saying if I design damper in this way, so this is a lower bound value of my damper. So this is a energy bound, input energy bound, and this is a supreme value of my performance bound. If we design this in this way, we can see that no matter what the signal looks like, the performance is always guaranteed. I'll show the examples in my later slides. And for the active control, for any given tensor structures and large morphing objectives, I have developed the nonlinear shape control law. So this is my nonlinear dynamics, and this is a nonlinear control law, which we call it aerodynamics. And combine these two, it turns out to be solving a linear programming problem with some of the constraints. So for example, the strings cannot take compression, so it's always positive. So here's a control law. And for the some of the systems, we don't have the dynamics, or the dynamics far away from the experiment model. So people usually go to database control. So what they do is they have a black box system and having the data from the input and output. So what people normally do is they do a system identification first. So to get the system matrices to represent this black box system and do control loss. So for example, the LQG control or other control loss. So what we do here is given the input and output data, we skip this term, we skip this step and go directly in the LQG control. And this is our control objective. So the first term is the tracking error. So for example, I'm doing a reference tracking problem. So this is a tracking error, and this is a tracking error and input increment during the trajectory. And the last one is input increment at the final step. And solving this problem, this is a control sequence that we need to give to the system to have the reference tracking. So all these parameters here, KK, and this XK bar is written in terms of the macro parameters. And macro parameters is computed from the input and output data. It represents the transient dynamics of the system. Another thing I want to point out is this kind of method is different from the machine learning method because machine learning method is like getting a system that is so for example, we have some input and we have some output. We generate a system that best matches the output Y for some given same input here. But our method is an exact match of the system. The macro parameters, we can guarantee that our physical system and the machine and the physical system have the same macro parameters. But machine learning is like getting close as possible. There's no exact match in their methods. And other methods like the least square methods is also like getting close as possible, but nothing can be guaranteed. This part is the resource location. So for the space system, we have the control performance bound. We have the control energy, and we have other control budget. So the budget is from the sensors and actuators. So how we are going to balance these three parts, the performance, control energy, and budget. And the question I'm asking is a problem feasible given the three values? And if it is feasible, what are all the solutions? So for example, this problem can be separated into three problems. So for example, the boss, they care about the money, and given the dollar bar, the budget, what is the least control energy and the best performance? And for the customer, we care about the performance, right? So given the performance bound, what is the least budget and the least control energy? And for deep space systems, the energy bound is normally a requirement because we have very limited solar panels that we can get electricity. So given the control energy, what is the least budget and the best performance? And these three questions can be written into this linear matrix inequality problem. And by solving this kind of problem, we will be able to answer the three different questions. All right, so for the results, this is a passive control example. So for example, we have the wind, we have the earthquake, and we can get the energy from the historical records. So we got the energy bound for from this part, and our customer can tell us what is peak value of So for example, the node displacement, right? So using the previously developed passive control method, we'll be able to find that no matter what the signal looks like, it can never exceed the output bound. And indeed, um, there exists a worst case, or the worst case is not unique. There exists the worst cases, I would say, that for example, the worst case signal looks like this, and with the same energy as the input as the other signals shown here, our algorithm can guarantee that the peak the performance bound is not exceed. So in this way, we can design the lower bound of the dampers, and no millions of Monte Carlo exercises are needed. For the active control, for example, the model-based control, we'll be able to do the large morphing objectives to the tensority structures. And for the database control, we compute the macro parameters from the input and output data and do the LQG control as shown here. There's estimation in the first 3 steps, so there's a jump here. But as you can see that we are successfully control our structure to the morphing targets. And for the balance resources allocation, this example shows that given the control budget and control energy, how to achieve the best performance. So for this kind of picture here, we show that so this is telling us that give you the money and we have control energy, and how to use this kind of money to buy sensors and actuators. And for the sensors, we capture the node positions. So for example, we can place the markers at the joints and use cameras to capture the node positions. So these are my sensors. And for the actuators, we are changing the length of the strings. So for example, we can use motors to change the length of the strings, or use SMA, which is shape memory alloy, to control the string length. And the algorithm is telling me that I should place my important sensors at here, and put my important actuators at the bottom. So this is reasonable, because it's like how we control our fingers, right? So for example, I'm doing precise operations. My eyes should focus on my tip of my finger. So these are my important sensors, and my bigger muscles are on the bottom instead of on the top. So my important actuators should be on the bottom. All right. And here we show some other interesting space projects. So for example, this is a drilling extraction automated drilling system. So this is a traditional rig for oil mining. And so as you can see, it has very heavy and large pillows on the 2 sides. And we replace this kind of structure with a tensority structure as shown here. So this is a this is a TD bar tensority. So T bar is efficient in taking compressive load, and D bar has a very compact size, so we can reduce the volume of the whole structure. So this is an animation show how it deploys. So the good advantage of this kind of structure is we can first we can deploy this kind of structure from a very compact size, we can put it in the rocket and launch it to space and do the mining operation. That's one advantage. And the other is after we do the mining operation, we can deploy, we can fold our structure and move it to somewhere else to do to drill other drilling points. So by using this kind of structures, we can decrease some weight and volume in a very efficient way. And the vibration of this kind of structure is much less than we expected, and it can successfully doing the mining operations for various rocks. And for this kind of project is a similar thing. For lunar mining operations. So as we know that for the lunar craters, the height is about 2 meters to 2 kilometers. And for this kind of height requirements, and also for the loading requirements on the, so for example, if we want to put communication devices, mirrors, and solar panels on top of the tower, we'll have different loading requirements, right? So for the height and loading requirements, we'll be able to design a family of lunar towers for different mining requirements. So for example, instead of using these long bars for the mining for designing lunar towers, we can increase complexity of the tensivity structure. So each bar becomes shorter and shorter. And in this way, we can also reduce the mass of the whole system. So this is the same picture as shown previously. And this habitat, as I introduced, this is housing 8,000 people, and it's a growth adaptable space habitat. So the whole habitat grows from 20 meters to 224 meters as economics allows at each time. And this is a 0G point, so it can be used as a docking port. And this is an agriculture region. And we have some side glasses that let the sunlight coming into the structure, and people are living here. It has been reported by Wall Street Journal, Voice of America, etc. So let me show you a video.
In the world of science fiction, filmmakers have created different.
Can you hear the voice?
Might look like more
Yes.
grounded, more
Okay.
space. This is a model of what it could look like, not just a ship, but a habitat that could sustain life for a long time.
All right. So all the inner structures are designed by tensivity structures. So for example, the inner pressure and rotational stiffness is provided by the double helix tensivity. And for the side structures taking the cantilever load is given by the tensivity mutual truss and etc. I would say. So in summary, today's talk, I presented the lightweight deployable aerospace structures. So we give a general approach to the lightweight deployable structure design with least mass. And after we have the structure, how to do the precise modeling of the dynamics of the integrated tensivity and origami structures with least computational cost. And for the controls, we have a series of efficient control methods with least dampers, sensors, and actuators. Thank you for your time, and I'm open to any questions you may have.